Hello, friends. So let's see if we can make this smooth. I'm going to go through the three major proofs from yesterday, and hopefully this will be helpful. And you've seen them already. You've struggled with them and suffered with me in the midst of them. And so now we can look at them with kind of a fresh perspective. And I've got a feeling things are going to click a little bit better. So let's get going here. Let's see, I'll use blue. So the first thing we were showing was an application of the result that every subgroup of a cyclic group is cyclic itself. And the application was to show that if I had a subgroup of the integers under addition, that subgroup H had to be of the form MZ, which is identical to this cyclic group generated by M. Now we know it's a cyclic group, but we're trying to find the specific form of it. So what we're going to do is construct that M. Oops, shit, my cable's getting weird. We're going to construct that M in the following way. So M is going to equal the minimum positive integer that is inside H. So H is the subgroup, right? And if it has one positive integer inside of it, it also has a negative integer inside of it because it's got its inverse inside there. And if it's got a negative thing in it and is less than zero, it also has the opposite of it in there. So we can always assume that if this thing is more than just zero, and we should assume that, we probably could do a case where it was equal to zero and just deal with that. In other words, M is zero, so that you just get this zero subgroup. And could have mentioned that yesterday. I guess I'm mentioning it now, but there is that trivial subgroup possibility. So I guess we just handled it. Now we're going to assume there's something besides zero in H. And that means there must be something positive in there because inverses are always included. So we're going to let this M equal the minimum of all the positive elements that are inside H, all the positive integers in there. And our claim is this, and this was the part I kind of screwed up. Just writing this claim out like this. So I'm going to prove that, and that means I have to prove two things, this and this. Let's do the second one first. This one's pretty low key because we literally are saying that M comes from H. It's an element of H. And once I have M in H, wow, we're getting weird orange red color there. Um, Once I have M in H, I know that every power of M is in there. In other words, K times M is in H because, like M plus M is in there and M plus M plus M, and then all the inverses as well. So that means that the cyclic group generated by M must be completely contained in H. If M's in there, all the multiples of M are also in there. So we got this guy knocked off. The other one is the tricky route. So what we're going to do now is I'm going to show that H is contained inside the cyclic group generated by M. Sorry, some garbage truck coming down the street. Um, and maybe you can't even hear that. Sorry, there was a lot of noise out there. So, you know, you know me, easily distracted. So, I'm going to take an element of H and I'm going to show that it has to be a multiple of M. And to do this, we use the division algorithm and divide h by m, like so. And that remainder there is going to be the thing that we play off of. And I'm going to rewrite that as R equals H minus MQ. So let's think about what we got here. H was taken from H. M is an element of H. We built it to be an element of H up here. So this is also in H because it's once M is in there, all multiples of M are in there. And we already know that from right here, right? We have that result. So this whole thing under closure must also be an H because H is a subgroup. But now we've got an element of H that is less than M. And the only thing that could possibly be is R being 0. So now if R equals 0, come back to this equation up here. We see that H must equal MQ. So in other words, that H that I took from the arbitrary subgroup H is actually a perfect multiple of M, and that means it is in the cyclic group generated by M. And now we've got the other inclusion that we need, and we can conclude that those two sets are equal. So that was the first one. And then the second one, I'm moving away from red. I don't know what I was thinking there. Let's move to just a straightforward black here. We had this result that G is cyclic. G is of order n. And we're going to assume that G is generated by some element A. And the result was this, that A to the K is the identity if and only if n divides K. So let's go this direction first. In other words, I'm going to assume that n divides K and show that A to the K equals E must follow. So if I assume n divides K, that means that K is equal to M times N for some M, some integer M. And now I remember, I think this is the one I asked you all to be able to prove for the exam. So when I wrote this down, I thought, yeah, we want to be precise about where that M comes from when we're doing a lovely proof. So once I have that, I can write A to the K equals A to the M times N equals A to the N to the mth power. And since the group is of order N, A to the N is E, and E to the M is E. So we've shown one direction. Now we're going to go the tougher direction. So we go this way, and that's going to be a division algorithm argument. So we're going to assume that A to the K is equal to E. Using the division algorithm, we can write K equals Qn plus R, and R is our remainder that's less than N. So then we come and we rewrite this expression here. So now I have A to the K, which is E. I'm just going to put that E over there. So E is equal to A to the K, but K is Qn plus R. And this is for some integer Q as well. So this is A to the Qn plus R, and we do a little rewrite on that. That's A to the N to the Q, A to the R. A to the N is E, again, by the order of the group being N. And so here we have E to the Q, A to the R equals E, A to the R equals A to the R. So getting kind of granular there. I hope I got enough room to finish this, and I think I might. Because what I just showed is that A to the R is equal to E, but remember that R is between 0 and N, not including N. Well, we know that the order of the group is n. And that's the minimum power, the minimum positive power that I can raise something to get the identity. So in other words, if I have b to the k equals e, if k is less than n, that can't happen. K has to be n or a multiple of n, which is kind of what we're proving, but it's what we've got here. Um, so the order of the group is n. That means a to the r can't equal e until you hit n. And now that we know that, that means the only other alternative is, and so let's write this out actually, since order of g equals n, let me scratch this guy out. Since order of g equals n, n is the least positive power for which a to the n is equal a to the, yeah, equals e. I don't like that notation. So since r is less than n, r must equal 0. And once I have r equals 0, I can go back to this expression and replace that r with 0. So this becomes, so becomes k equals qn. And that, of course, now implies that n divides k. And we have our result. Lastly, the final result was Theorem 413. And Theorem 413 says that G is cyclic, order n, and G is generated by A if b to the k, blah, blah, if b is some element that's equal to a to the k. So b is an element of this group G here. Then the order of b is k over d, where d is the GCD of k and n. So the proof goes like this. We want, and this was the move I missed at the beginning. We want the smallest positive m such that b to the m is the identity. And that's the order of b. That is the definition of the order of b. So what would this mean? We're going to translate this back into this a to the k form that we have. So b to the m, let's put e equals b to the m equals a to the k to the m equals a to the k times m. And then we think back to the result we just proved, that since the order of the group is n and a to the km, woo, made that sloppy, a to the km equals e, then n must divide km. So now we've got our kind of pivotal division fact here, and I guess this is proposition 412, actually, that we just used. Um, we have n divides that. So now I'm going to divide both sides of this by d. In other words, I'm going to replace n with n over d and k with k over d. And then I have that times m. And I can do that because d is a divisor of both those things, and it's the largest such divisor. That means once I pull this common divisor out of n and out of k, they have nothing in common anymore. They have no common factors. So there's no way that n over d could possibly divide k over d. But this must be true because this is an integer and this is still an integer. You know, when I divided by d, that worked out perfect. These aren't weird fractions or anything. So if this statement is true, it must be that n over d divides m. It must be true that that is the case. And since m is the smallest positive number, that we're looking for the smallest positive m, so that this is true, the only answer is that m must be n over d. And if m is less than that, n over d can't divide it. So we now have our result that the order of b is n over d. Well, that went better. And kind of feeling a little sick today. I thought about going on, but I think I'm going to call it there. And I'm going to post this and send y'all an email. So I hope that helps. Hope that helps, friends. And I will talk with you all soon. I'll be making some videos about all this stuff that I've assigned to you. So I was kind of thinking I might work some of the tougher review problems like this and then just post the videos for you. So we'll see how that goes. That's kind of the plan right now. And all right, be well. Bye.